Hello everyone, Ross Satchell from Microchip Technology again. Today we're going to take a look at how to import Atmel Start projects into Mplab X. So first, an overview of this demo project. We will be using an AT Tiny 1607 Curiosity Nano. We will have a potentiometer connected across VDD and ground, with the wiper connected to pin PA1. We will use a real-time counter, or RTC, to trigger an ADC, or analog to digital converter, read every 100 milliseconds. If the reading is different from the previous reading, then we will print the new reading. Using MPLAB Data Visualizer plugin, we don't even have to leave Mplab X to do our debugging. We will do the peripheral setup at start.atmel.com. We will add a real-time counter, or RTC, and we will set it to 100 milliseconds. To do that, we need to calculate the number of cycles. We will be using the 32 kHz internal oscillator, which has a period of 30.5 microseconds. Doing a quick bit of math, we find the number of cycles that we need for 100 milliseconds is 3,279. This is the value we will use for the period register. Then we will add an ADC peripheral, and we will use the Adc Basic driver. We will read from pin PA1, and we will use VDD as a reference voltage. And finally, we will add a Usart, and we will enable printf support. So now, let's go to start.atmel.com. Click on Create New Project. Since we are using the AT Tiny 1607, we can filter the results here by typing in 1607. We can see there's two available, both in the VQFN package, which is the package used on the Curiosity Nano. So either of those will be fine for us. Once you have selected one of the devices, click Create New Project. That will bring us to the project setup page. Now we can start adding peripherals. So now click Add Software Component. And we can see we have middleware and drivers. Now, the peripherals are under drivers, but first let's take a look at middleware. There's lots of libraries in here for various different micro-click interfaces, so these can come in handy for other projects that we work on. Now we will click on drivers, and we can see under that all of the peripherals that are available on the AT Tiny 1607. We want an ADC, so click on the plus sign to add it. You can see it's now added down the bottom. Now we need an RTC and also a Usart. So you can see three peripherals selected down the bottom, and we can see we have one of each peripheral. Now you can change the number of instances of a peripheral provided that your device supports that. Finally, click Add Components. We can see our three peripherals added here. So let's start with the ADC. Click on the ADC 0 button. That brings up all the settings for the ADC. Now, as I mentioned earlier, we will be using the basic driver. Our component signal will be connected to pin PA1. And we can see that corresponds to A in 1, which is analog input 1. The other thing we needed to do was set up the voltage reference. We will be using VDD as our reference since the potentiometer is connected across VDD and ground. Now we can go up to our RTC and set that up. Click on the RTC 0 button. First of all, let's put the period in, 3279. So with all of these fields, you can enter the values in binary, octal, decimal, or hex, and it will auto-detect. So it's automatically detected that we've entered the value in decimal here. Next, we need to enable the RTC. We then need to include an interrupt service routine, or ISR, harness in the driver ISR file. And we need to enable the overflow interrupt so that when the counter overflows at 3279 cycles, or 100 milliseconds, that will trigger the interrupt for us. Next, we need to set up the Usart, so click on the Usart 0 button. All we need to do here is enable printf support. Just take notice that the baud rate is set to 9600. Finally, we need to click on the CPU int button. We need to enable the global interrupts, otherwise our RTC interrupt will not occur. So now that we have done all that, we can export the project. But before we do, let's click on the View Code button that shows us all of the code that's been generated. So if we click next to Examples, then Include, we can see the two examples generated for us. There is an Adc Basic Example and a Usart Basic Example. We also have under Include the header files for the project, such as Adc Basic Header File, as well as start pins, or in other words, how the I/O pins are initialized. They also have the RTC header file and the Usart header file. And then there's the accompanying source files for those header files. We also have the driver ISR file in which we find the interrupt service routine, which has been passed the parameter of the RTC count vector. And that's where we will be setting up our ADC reads so that they occur every 100 milliseconds. And finally, it has an outline of a main.c file. Now let's close that window and click on Export Project and give the project a name. I'm going to call it Import Start, and then click Download Pack. That downloads a file with the extension atzip. Now open up MPLAB X, give it a moment to load up, and then connect the ATtiny 1607 Curiosity Nano with your USB cable to your computer, and within a few seconds you should see the kit window with a picture of the ATtiny 1607 Curiosity Nano. You'll also find there a user guide, schematics, datasheet, and the kit homepage. If the picture of the ATtiny 1607 is grayed out, unplug the Curiosity Nano board from your computer and restart MPLAB X. Once it is fully restarted, plug the Curiosity Nano board back in and you should now see the kit window. Now in MPLAB X, we're going to import the Start project. Click on File, Import, Start MPLAB project. Then you will get the following pop-up where you'll navigate to the downloaded file and then click Next. Now we can see the selected device is grayed out since we've already selected the device using Start. Click Next, and now we can select our programming tool. Select the ATtiny 1607 Curiosity Nano and then click Next. Now we select our compiler. I am using XC8 and then click Next. Then we will give the project a name and a location. Click Next, and then we have our summary of the files that will be generated. Click Finish. That then goes and sets it all up for us. We can now open the project directory and we can see there that we have some header files inside that. We also have the examples that we saw were generated in Atmel Start. We have an Adc Basic Example and a Usart Basic Example. So double click to open the Adc Basic Example header file. And also, if we scroll down, we can see all of the other header files are included, as well as the source files. And further down the bottom, we have under the source files, the driver ISR file, which is where the RTC interrupt will be called. So let's open that. And then there's also the main.c file, so open that one as well. First thing we are going to do, we'll go to the Adc Basic Example that we opened, and we can see that function call that we saw earlier in Atmel Start. If you hold the Control key and then hover your mouse over the function, you will see it changes color and it's now underlined. So clicking on that takes you to where the function has been defined. And we can see inside that function, there is another function called ADC0getConversion, and its return is a variable called ADC0measurement. So use Control-click again to take a look at ADC0measurement, and we can see it's of type ADC result. So that's the function we want. So now copy that function call. Now we're going to go to our driver ISR file that we opened a moment ago. Inside that file, we can see the interrupt service routine, or ISR, for the real-time clock counter vector. Before we do our ADC function call, we need to do the include statement for the ADC basic header file so that the compiler knows where to look for the function. To do that, we type #include ADC and then hold down the Control key and press spacebar, and that shows us the header files that we can refer to. So we want to use adcbasic.h. Next, we want to set up a variable in which we'll save the result of an ADC read. So you saw before the type ADC result. So now typing ADC and then pressing Ctrl and spacebar, you can see the options that are available to us. And at the bottom of the list is ADC result. That's the one we want. And now let's give the variable a name. I'm going to call mine val. Now inside the ISR, we're going to type val equals. Now we can paste that function. And also remember that the potentiometer is connected to analog input 1, so we need to put a 1 here. And don't forget the semicolon at the end. Let's quickly build that to make sure there are no errors before we go any further. There we go, build successful. Okay, next we go to the main.c file. So in the main, we're going to be doing some printfs. So let's start by including the standard IO header file, Control space to autocomplete. Now we need to set up an external variable, which is of type ADC result with the name val. We also want to set up another variable to save the last value. Remember, we're going to compare the current value and the last value, and if they're different, we will print val. So we need a variable of type ADC result. But what is ADC result? Well, just like before, we can use Control-click to follow where it's defined. And that takes us to the type def, and we can see from here an ADC result is actually an unsigned 16-bit integer. So I'm going to make my variable an unsigned 16-bit integer, but you could also do ADC result. I'm going to call this one last val. Now in the while one loop, I'm going to check if last val is not equal to val. If that statement returns true, I will call printf, and then inverted commas, value, and then %d \n, and then pass it the variable val. Finally, we need to save last val as val. Now let's build that. We can see the build successful message. Now let's make and program the device. If prompted, select the device from the list. So now we can see it builds the project again. Now it's connecting to the programmer. And then we can see the programming complete message. Now open the MPLAB Data Visualizer plugin. If you have not installed it, the link is in the description below. In that, we can see the AT-Tiny Curiosity Nano. We have COM31 in my case. You may have a different COM port number. Now we click the play button and we get the message COM31 streaming started. And then finally, down at the input selection, we need to select our source. We can see COM31 on AT-Tiny 1607 Curiosity Nano. Click on that, and now when I adjust my potentiometer, I can see the values changing in the terminal. And that's how easy it is. So don't forget to smash that subscribe button, as well as click the notification bell. And if you enjoyed this video, please give it a like or a comment. Thanks for watching.